Good morning, everyone. As per usual, I will apologize for any background distractions. I like to try to record a lot of my lessons, and especially if I'm doing experiments or things like that, at home, where I think there will be fewer distractions to be in the video later. But I do have distractions in the form of, toddler and cat. So there's that. Today we get talking about the warm and fuzzy part of science, or at least the warm part of science. So, with that said, we are starting our unit today, which is still tied into our energy unit because we're getting a little more specific about one type of energy. We are starting our unit on temperature, thermal energy, and heat, getting more detailed into those. So I'm going to start you guys off with a real brain buster. Which of the following do you think has more kinetic energy in the form of thermal energy? Remember, this is a type of kinetic energy, but one very specific one. Which do you think has more? More thermal energy associated with heat. This delicious pumpkin spice latte, piping hot. Lovely. Or this even more lovely, beautiful Alaskan glacier. This is in the Johns Hopkins Inlet of Glacier Bay National Park. I was there a couple of years ago. We'll talk about why the ice is blue at some other time. This is about a 500-foot tall just wall of ice that then runs back into a giant river of ice that goes on and covers many, many, many square miles. So again, thinking about thermal energy, the energy associated with heat, which do we think has more? Piping hot latte? Beautiful Alaskan glacier. And what a combo, am I right? All right, take a good 10-15 seconds and give yourself a brain buster there. All right, so I got my Jeopardy music in. I'm happy. For those of you who guessed the pumpkin spice latte, no latte for you, you are incorrect. Those of you who guessed beautiful glacier, and again, just stunning, you are absolutely right. And at this point, you're probably like, whoa, lady. What? Because that glacier is made out of ice, and ice is coldy cold. Like, it's like literally a wall of ice. That's about as cold as we can get, other than that empty void where Miss Johnson's heart is supposed to be harsh. And a piping hot latte, you literally just described as piping hot. Obviously, it has more heat. Well, this shows me that I need to teach you what heat actually is. Welcome to my home. All right, so when we are talking about thermal energy, I have some stuff up here. Thermal energy, what I asked you about, is the measure of kinetic energy in particles of an object. So we know objects are not just like one big solid thing, right? They're made out of tiny little particles, atoms, molecules, blah, 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 and all those are together. When we're talking about thermal energy, we're talking about the total amount of motion at a molecular level. So to make this simple, the more mass something has, the more thermal energy it has. Because if we're looking at it in terms of molecules, more molecules mean more thermal energy. So with that being said, as much as I would love for this pumpkin spice latte to stretch over the course of several hundred square miles and be many, many, many hundreds of meters deep and just basically never run out. Dreams. It's not the case. It has nowhere near as many molecules in it as does this beautiful glacier. This glacier has so many more molecules that overall it has a lot more thermal energy. So the question then becomes, like, why is it the case that this feels so much hotter? If I go up and touch ice, I'm going to be like, ooh, cold. If I go up and stick my hand in a hot latte, first of all, gross, and secondly, I'm going to go, oh, warm. It's because of temperature. Temperature is a little bit different. When we talk about heat, we're going to be talking about, and please excuse my high chair holder here, the movement of thermal energy from a warmer object, warmer meaning an object with a greater temperature, to a cooler object, one with a lower temperature. So that's when we have to start thinking about what temperature is and how it relates to heat and thermal energy. Temperature is a model of, or a measure of how fast the molecules in something are moving. So we know that speed, along with mass, is one of the things that increases kinetic energy. This makes sense when we think about the glacier having more mass and therefore having more molecular kinetic energy and therefore more thermal energy. When we think about how fast the molecules in something are moving, that's where we get temperature. The molecules in this piping hot coffee are moving much, much, much faster than the molecules in that glacier. Therefore, this has a higher temperature. It is hotter. However, it does not have as much total thermal energy. And we'll get into that a little bit more as we see things going on. We'll look at what happens when we see things start to heat up, when we see things melting, when we see things sizzling, when you get to go to Miss Johnson's Learning Kitchen, which you'll learn about later, and Miss Johnson's Learning Kitchen is dangerous, because you'll see me get burned a lot, but hopefully you'll learn things in Miss Johnson's Learning Kitchen. I'm very committed to making it work, but, you know. Anyway. So when we are measuring temperature, that's where we want to start, okay? We know we're talking about thermal energy overall. We know that when we're talking about heat, we're going to be talking about thermal energy moving from a warmer place to a cooler place, and that's the only direction it can go. We'll get to that in a minute. We're going to have to be talking about temperature while we do this. Temperature scales are a little bit different. Here in the U.S., we use what's called the imperial system, which is strange because the country that invented the imperial system doesn't use it anymore. It's really just us in the Bahamas that use degrees Fahrenheit. Most of the world, and especially the scientific world, uses degrees Celsius. So I want to take a second and address that elephant in the scientific room about how we don't use the same measuring system as a lot of other people. But if you want any kind of career in the sciences, or any kind of, to be able to really go on and study the sciences, you have to get familiar with degrees Celsius. So degrees Celsius can be a little confusing at first because the numbers look so different from what we're used to in a lot of things. Sorry, buddy. Sorry, I had to just take something back from the child. So, for example, anyone's not a word, anybody know what the freezing point for water is in degrees Fahrenheit? I'm going to pretend that you're all answering that it's 32 degrees, which would be correct. In degrees Celsius, it's 0. We start with 0 as our freezing point, which seems to me to make a lot more sense. And we do have a formula for calculating and going from Fahrenheit to degrees Celsius. So looking at this, x degrees Fahrenheit, sorry, I'm mirrored, so I always do this, x degrees Fahrenheit minus 32 times 5/9 will give us our degrees Celsius, and I just use y as my other variable there. So let's try this with one point that we know, which is the point for freezing. So we know 32 degrees Fahrenheit is our temperature for freezing. And if we subtract 32 from that and multiply by 5/9, we should get our degrees Celsius. So 32 minus 32 is obviously 0 times 5/9. Anything times 0 is going to equal 0. And that gives us 0 degrees Celsius. Okay, so we can check it with that and see that it works out just fine. Let's try it with another number. The temperature outside right now, it's 84 degrees. Not my cup of tea. I'm a cool weather kind of person. Okay, so let's try that formula again. I'm going to say 84 degrees Fahrenheit minus 32 times 5/9, which is 0.555555 repeating in decimals, equals whatever my degrees are Celsius. Okay, so 84 minus 32, I can kind of do that math in my head, but, take a minute, think about it. So we'd set it up, have 4 minus 2. Let's write it out the other way just to make it a little easier on ourselves. 4 minus 2 would give me 2. 8 minus 3 would leave me with 5. So I'd have 52 times 5/9, or 0.555. And as I go through and look at that, doing that multiplication, I'm going to come out with about 28.8, or we could maybe round that up to 29 degrees Celsius. So if you're talking about like a 30-degree day, a 29, 30-degree day in degrees Celsius, you're talking about a very warm day. If you're talking about it in degrees Fahrenheit, you are talking about a pretty chilly day, right on the cusp of freezing. So we'll do some more practice with that math a little later, but I just wanted you to kind of get the feel for why the numbers seem so different. Like a nice day, 70 degrees in American or the imperial system, degrees Fahrenheit would be, 70 Fahrenheit comes out to about 21 degrees Celsius. The euthermic temperature for the human body, meaning the normal or optimal temperature for the human body, is widely considered to be 98.6 in Fahrenheit. In degrees Celsius, it's about 37 degrees. So 36, 37 degrees, you're good in degrees Celsius. Here, you're like quickly becoming a popsicle, and there's a good possibility that you are part of the undead if you're ranging that in Fahrenheit. So should it be the case that you realize your temperature is 37 degrees Celsius, know that you are healthy. If it is the case that you realize your temperature is 37 degrees Fahrenheit, you might be a vampire. And just kind of be careful with, sunshine, and, don't bite anyone. It's just not hygienic. Okay. We also have the Kelvin scale. We don't really use it a lot. I'm not going to get into it too much. We do use the Kelvin scale to reference one temperature, which is called absolute zero. And this is considered the lowest temperature that anything could ever get, where all molecular motion stops. Fun fact, we've never, that we know of, humans have never discovered something that was actually at absolute zero. There is always some minute amount of energy going on at a molecular level. Kinetic energy, thermal energy going on at a molecular level. Okay, so we want to get some practice in with that, and we want to remember that in the United States, we use Fahrenheit. In other places, we tend to go with Celsius. And this is just kind of how things are for the moment. But in science class, we will be using the metric system in degrees Celsius, also called degrees centigrade, quite a bit. All right, so getting into thermal energy a little bit more. So different objects that are the same temperature can have different amounts of thermal energy. Why is this? I wonder if I can play my Jeopardy music again. Okay, we got that instead. So why is this the case? Two objects, same temperature, different thermal energy. Well, we know that temperature has to do with the speed of the molecules, right? And we know that thermal energy is talking about kinetic energy. So if we know that speed is what causes temperature, then what could be the other determining factor? Sorry, I'm still not used to the mirror sensation. So if speed is determining our temperature, what is the other thing that could cause an object to have more thermal energy? If we're still thinking about types of kinetic energy, we know it's going to be speed and mass. So larger items, same temperature, mass can increase and does, in fact, increase thermal energy in objects of the same size. So, say, for example, we have, I'll use the example that's in your textbook because you're going to have to read this anyway. Say, for example, we have two pies, okay? They are the same temperature. They have both come out of the oven, and they are a piping hot 350 degrees Fahrenheit or 176 degrees Celsius. So they come out of the oven and are sitting there side by side. One has twice as much thermal energy as the other. What does that tell us? It tells us that one pie has twice as much mass as the other. And I want the bigger pie, depending on the pie. So that's something to consider. The mass of things given the same temperature will change the amount of thermal energy. Similarly, if we have two things of the same mass, what will increase the thermal energy? The temperature. All right, so let's talk about heat. Heat is a little bit, different. Heat is actually kind of talking about the transfer of thermal energy. Remember, thermal energy can be transferred because it's a type of kinetic energy from a warmer object to a cooler object. So if you grew up anything like I did, you always have at some point an adult yelling at you. And actually, I still have this happen all the time because I turn the air conditioning on and then open a window, which is not environmentally friendly, but it's very comfortable sometimes. You'll always have somebody say to you, stop, close the door, close the windows. You're going to let all the cold air out. You're going to let the air conditioning out. Guess what? It doesn't work that way. Heat energy always moves from a warmer place to a colder place. So when we're looking at direction, it goes from warmer to colder, higher temperature to lower. So if we have, for example, the air conditioning, it's probably hotter outside than it is in your house. Right now, my AC, sorry, I have a smart thermometer, thermostat, I have to wave at it, is set to 55. What on earth? No wonder. Okay, that's weird. That shouldn't have happened. I think my house might be taking over and trying to rule me. This is how it starts. This is how the robot apocalypse starts. Okay, so we're looking at things always going from a higher temperature to a lower temperature. If I actually set up a device to measure the temperature in my house and measure what was going on when I opened a door, hey buddy, you're okay. You just went boom on your butt. Sorry, we had a little boom on the butt incident. I'll be right back. Hey, friend. Hey, come here. Boom on your butt. Boom on your butt. Okay, so, and I will show this in an experiment later. If I actually go and open my door, what I'm going to see is that warm air rushes into my house because, again, it is moving from a warmer temperature outside where it's 84 to my house that I usually keep at 68. And if I put something in the doorway, what I'll see is that the air conditioning is not actually leaving, the warm air is coming in. In winter, you can let the heat out. That actually happens. You're not letting cold air in. You're having heat move away from your warmer house and to the colder outside. Thank you, Betty. Sorry. That's something that's really important to remember. When we talk about conduction, when we talk about convection, when we talk about radiation, these are ways that heat moves. In all of those circumstances, we're going to see heat moving from areas with a lower temperature to areas, or with a higher temperature to areas with a lower temperature. When I pick up my hot drink and I drink it, it tastes warm because it is transferring heat to me. I am colder than the drink. When I grab a glass of ice water and it feels cold against my hands, that is because I am transferring heat away from my hands to the ice water. So that's kind of how those things work out. So I think that gets us pretty well caught up on where I want us to be now. The key things that I want you to take away is that thermal energy is overall kinetic energy at a molecular level, and it is impacted by both speed in the form of temperature and mass in the form of, mass. So the size of things has a big impact on how much thermal energy there is. Temperature is a measurement of speed of molecules. If molecules are moving faster, they will have a higher temperature. And I especially want you to remember heat always goes in the direction of warm to cold. Warm to cold. That's always how it's going to go. Really cold is just the absence of heat. There's no such thing as cold. There just isn't a lot of thermal energy there. So that thermal energy will move. Heat is the movement. Will move toward the area where there is none. Everything in nature tries to find a balance. So we'll be looking next at the different ways that heat transfer occurs, and we'll see some experiments and demonstrations to go along with that in Miss Johnson's Learning Kitchen, which is dangerous because she's already had to use quite a bit of blister cream on her hands because of what the burns, because of all the hot oil, and because she touched a hot pan to prove a point about conduction. It's going to work. It's going to be so good. One day. All right. Until then, my friends, peace out.